Hello, welcome back. In this video, we will take a look at part one of the multiple linear regression. So first thing, we will open the new file and then go to Markdown. So that's, and then here I'm going to call this multiple linear regression part one. Yeah, I'm going to save it as a PDF file. Okay, and then click on OK. And then here we, so let's see. Let me see if I can read it to PDF file. And I just checked it works well. So let's get started. So let's first of all, I'm gonna delete all these unnecessary lines first, and then we're gonna take a look at Penguin's data set. Okay, and here we're gonna need some. So let's get a coding block. And we will need a couple packages. One of them is library ggplot2, and the other one is library Palmer Penguins. Now we're going to do data penguins, and also add penguins. And then so let's close the coding block. Let's run this code for a second. So look at the output, right? We get a this Palmer penguin data set. This logic that 3 different species: Adelie, Chintrap, and Gentoo, 3 different islands, and then we have BO length, BO depth, flipper length, body mass weight, sex, and years. Those are the variables we have here. And okay, now next thing, let's I'm gonna clear these graphs. Okay, outputs. All right. Now next thing, let's check the independent variable flipper length. So first thing, get an overall graph, right? ggplot. So that's why we need a ggplot package earlier. Penguins. Statics. X is the length, millimeter. So we are predicting we're using the flipper length to predict the body mass, which is the weight of the penguin. Body mass gram plus G on point. Okay. And then this is the first graph. I'm going to also show you, we're going to create another graph based on this, but it's a little more sophisticated. So I'm going to copy this code. And then here I'm going to put in color. I will separate by 3 different species. So we do color equals species. And G on point, that's good. And G on smooth. And we try to fit a linear regression model for these 2 variables. Method equal to linear model ln c equal to false. Right, let's run the code. And basically we have 2 graphs. First one, basically we look at the relationship between the flipper length and also the body mass. There's a linear correlation between these two variables, but it's not very strong. Okay. But for the second variable, since we separate into 3 different species, it looks like it's a little bit better, right? So blue one is Gen 2. I would say medium strong correlation. And then chin strap is a green one, similar, right? Similar to Gen 2. Also, the red one is for Adele. Looks like Adele has the weakest. Looks like it has weakest, maybe, yeah, close to weak. Medium correlation between the flip length and body mass. So by separating by 3 different graphs, we can see a clear picture. So I'm going to close out this block right here. Okay. Now let's check the other variable. Check the bill length and then bill depth, one at a time. Next thing, let's check variable. Oh, actually, you know what? It's so much better if I just copy this coding block, copy the whole thing. I just change the variable accordingly. So here, change this to bill length. Now here, just change. I don't need this anymore. Just delete that. Now we are doing this bill length, just changing this x variable to bill length. One variable stays the same, color, species, GM point. Yeah, everything else stays the same, and let's run the code. And this is the graph. Look like Gen 2 has the strongest correlation between the bill length and the body mass, the weight. And Adele probably is the second, is close to Gen 2. Chin strap has still medium, but it's weaker than the other 2 species. And that's basically what we see for the second variable, bill length. I'm going to clear the graph. Now one more time, let's check the last variable. Bill depth. So I'm going to reuse all these coding blocks. And now it's a bill depth. To change this variable to bill depth. And then here change to bill depth. And then let's run the code one more time after equals. Yeah. Okay. Yeah, let's run the code. And this is the graph. Look like Gen 2 is totally different from the other 2 species. Adele and chin strap are overlapping here. So look like Adele and chin strap almost have the same, almost have identical correlation between the bill length and then also the body mass. And Gen 2 also has a medium strong correlation here, but it looks like Adele and chin strap are slightly stronger correlation between those 2 variables. Okay. Then we get this summary output. And it looks like flip length millimeter is a highly significant predictor here as 3 star. Right? So it's a very significant predictor variable. Yeah. And also adjust R square, right? R square is 0.759. That means 75.9% of variations in the body mass and the weight of penguin is explained by the flipper length. And then if you look at overall F-test, it's highly significant. The p-value is 2.2 times 10 to the negative 16 power. So this model is a pretty effective model. So according to the output, we look like the model is pretty effective because 75.9% of variations in body mass is explained by the variation in flipper length. Right, that's a quick summary about this. Now let's create a linear model using 3 different variables. Okay, so I'm gonna just copy all these blocks. Paste it here using 3 variables, which is the flipper length, BO length, and BO depth. And here we just add those 2 variables. And we're going to call this model 2. Okay. Change that to model 2. And let's run the code. And we check the outputs here. It looks like here the only significant predictor variable is the flipper length because the t-score is very large and the p-value is extremely small. And then for the other 2 variables, BO length and BO depth, they are not significant at all because the p-value is very large, which is greater equal to 0.05. So that means we should drop the other 2 variables, BO length and BO depth. And we look at a multiple R square compared to the previous model, since we're adding 2 predictor variables, and then the looks like adjust R square did not go up too much, right? It just go up a tiny bit. So that means these 2 additional predictor variables are not effective. Okay. So in this case, we're going to say this, adding 2 additional predictor variable does not help too much. Maybe we should drop those 2. Drop those 2 predictor variable, those 2 additional predictor variable. Maybe drop in the BO length and BO depth. Because adjust R square did not go up too much. The adjust R square does not go up too much. Yep. So and let's create a third model. We will call this with all the variables, right? So here I'm going to just recycle this, we'll copy this, paste it here. The last thing we're using all variables, all predictor variables. And then here we will call this model 3. We can also call this full model. Let's call that model 3. And then right here, I'm going to delete all those variables. And then if you want to get the full model, you just do dot. Right. This dot indicates we're including all the predictor variables in the data set. Let's run the output and see how that goes. And look, when we look at the outputs, look like species change trap and then species gen 2. They all kind of like significant predictors here, especially species gen 2 has 3 stars. And then island are not significant predictor at all. And then BO length, BO depth, pretty significant predictor variables. And then also the flipper length now still remain as a very highly significant predictor variable, and then sex is highly significant predictor variable, and the year is not extremely significant, but it's a good predictor here to use. And then that means there's a kind of like internal interaction between those variables, and that's why we see the effectiveness of each predictor variable changes when we account for all predictor variables. And also, if you look at adjusted R-squared, then now this time it go up about 12%, right? That's pretty good improvement here. So this full model definitely is so much better. Okay, so and just quickly comment this, right? So the Model 3 is much more effective, much more efficient model to predict body mass gram because adjusted R-squared go up significantly. Adjusted R-squared go up about 12%, and that is a significant improvement. So that's basically how we build a model, and also we can use AIC to check the effectiveness of the model, or like check how good each model is. And then AIC is what they call the Akaki information criterion. And then AIC measures the relative amount of information lost by a given model. The less information a model loses, the higher the quality of that model is, right? So now, next thing, let us check AIC, check and compare AIC values. So now get a coding block, and then just type in AIC, and looks like model 1, model 2, and model 3. Let's just close the coding block, run the code, and then it looks like model 3 has the smallest AIC values. If you look at model 1 and model 2, there's no significant improvement, right, on AIC, but from model 1, model 2 to model 3, and there's a significant reduction of AIC. So again, model 3 is better. We can also check the BIC values. BIC is called what they call the Bayesian information criteria, and let's also check that BIC values, and then change the BIC. I should see a similar result here. Let's see if that is true. Yeah, if you look at it, looks like it's very similar outputs. Model 1, model 2, no significant improvement, but a model 3 becomes a very effective model based on the BIC values is a lot smaller compared to model 1 and model 2. So the two information criteria confirm the same result. So based on AIC, according to AIC and BIC, model 3 is a superior model. It looks like in this code, it looks like there's a constant variance, right? Because we see a random plot, and then also since it's random plot, so normality is not violated. So the residuals are normally distributed, and also has a constant variance. The residue, so the conclusion here, note. Very good diagnostics. Residuals have constant variance, and then normal distribution. Now let's create a multiple linear regression model. The multiple linear regression model with a subset using only two species of Delhi and Gentoo. See how that goes. Right? We can actually do that. So let's run the code. And we're going to call this model 4. Yeah, we are running a linear. Yeah, so before that, right, we need to get this, call this penguins 2. Right? Get a subset with only two variables from penguins data set. And then the species we are selecting is Delhi and also Gentoo. Okay, so let's do that first. And then after that, we just run the model 4. Okay, so we call this model 4. And then it's a linear model. Body mass, gram, body wave, slipper length, millimeter plus BO length, millimeter plus BO depth, millimeter. And here we are using penguins 2, right? The new data set called penguins 2. And then we're going to get summary of the model 4. See how that goes. And then let's close the coding block. Let's run those code. Now if you check it, since we're using the subset, now all three predictor variables becomes highly significant. Meaning when we just account Delhi and Gentoo, there's a very strong correlation between the fiber length, BO depth, and also the body mass. And also it looks like adjusted R square has improved significantly. And each predictor variable now are highly significant, as you can see. And an overall F test is pretty significant. So when we use using the subset, all three predictor variables becomes highly significant, and a multiple linear regression model is pretty effective. That's what we see from the updated model. Now let's make a prediction using the same measurement from previous one. So let's copy this. So we're going to make prediction using the model 4, here. And all we have to do is change this object to model 4. And let's run the code. So now because it's much better model, so we get much better prediction here. 5,585.026 grams of weight. Let's run the second example. Comparing. Okay, so let's see how that. Let's take a look at second example of models. Now we will run the multiple linear regression. To predict flip length millimeter. So let's get a coding block, call this model 5. Linear model. We are predicting flip length using VO length millimeter. Body mass and also the species. And data we're going to use the Penguin tool. And let's get a summary output of model 5. And if you examine each individual independent variables, they all look highly significant. And especially Gen 2 species, Gen 2, it's superior, right? It's super significant. And the other two is also body mass is also highly significant. VO length is significant as well. And then if you look at the Jersey R squares, 87.96% of the variations in flip length is explained by those three, by the variation from the other three variables. And the overall F test is also highly significant. So the overall model it's pretty good, right? So the overall model is highly significant. So the interesting thing in the multiple linear regression is there's an interaction effect on those variables, right? And then that changes dynamic of the effectiveness for each predicted variable when the interaction effect kicks in. Now let's create a model using the variable species to interact with the VO length. Let's see how that goes, right? We can actually do that in the stereo. So let's create a model using the variable species to interact with VO length. And let's get a coding block. Okay, and then I'm just going to use the previous one. If you change this slightly, okay, let's copy this coding block here. And we're going to call this model 5A. Okay, it's kind of like a sub under the model 5. And here we're going to interact the bill length millimeter with the species. Multiply by species. I'm going to get rid of the species here. Okay. We're still using the penguins 2 data set. And let's see how that goes. Okay. Let's run the model. Now, as you can see from the output, now bill length becomes insignificant due to the interaction. So now the p-value is 0.1850. T-score is very small. So that means it's not a significant predictor. And the species Gen2 is not a significant predictor as well. And then body mass is still remain a significant predictor, highly significant predictor. And the interaction is pretty significant, but not very strong, right? See, it's only one shot, so that's a significant interaction. That's an interaction between bill length and the species, but it's not super strong interaction. But if you look at the adjusted R-squared, 88.14% of the variations are explained by this interaction model, taking into account the sample size and then the number of predictor variables used. Still, overall test is highly significant. Next thing, let's create a model using the species to interact with body mass. Okay, so I'm going to recycle this code, just copy that, and then just modify slightly underneath it. So here, I'm going to use species to interact with the body mass. So yeah, let's just get rid of this, cut it and paste it. So we're going to call this 5B, model 5B. And then we're going to interact body mass with the species. And then it's still data equal penguins 2. This is 5B. Let's run the model. And if you look at the overall model, bill length is highly significant. Body mass by itself is highly significant. But the interaction, there's no interaction between the body mass and the species. And species is not a significant predictor at all. Okay. So that means, yeah, there's no interaction. Look at the adjusted R-squared, actually, it came down slightly, right? So the actually previous one is probably slightly better, but not much. Now the third model, I'm going to using the species to interact with both variables, both bill length and also the body mass. Okay. So here I'm going to use it, species to interact with this and body mass. Let's see how that goes. So now here times species and then times, we're going to call this model 5C and then multiply by species. Penguin 2 and then let's change to model 5C. Let's run the code. Now in this updated model, looks like only body mass gram is highly significant. The rest of them are not significant at all. Bill length is not significant. Species is not significant. There's no interaction between the bill length and the species Gen2. There's no interaction between the body mass and also the species Gen2. And you look at the adjusted R-squared, it's almost remains the same, right? No big change. So again, there's no interaction between those three. Okay. Now let's check the AIC, BIC values of all three models. So I'm gonna clear the outputs, check or compare the AIC and BIC values of all three models. Here, got a coding block, curly wave R, and put in AIC, and we do model 5A and model 5B, model 5C, and also the BIC. So I'm going to reuse this to change A to B. And then close coding block and check it, see what happens. You look at AIC, model 5A is slightly better, but not much. The margin is very small. The difference is very small here. But model 5A is the best. And then look at the BIC, similar, right? Similar outputs. Model 5A is slightly better compared to the other two. So model 5B and 5C is less significant, less effective compared to model 5A. So in this case, according to both AIC and BIC, both AIC and BIC, the model 5A is the best overall model. Since that both AIC and BIC are smallest of the models. Now let's make prediction. Make a prediction for flip length. Given that BO length equal to 50 millimeter and body mass equal to 4,000 grams, and is of the species adapted. And let's run the code to see how that goes. Here, curly wave, and then let's put in the predict R here and then predict. Object is its model 5A, new data frame, BO length. Now we can just copy that. BO length, body mass, copy those two, and then the species, let's type in species equal to Delhi. Yeah, let's check, see that close the coding block. See what happened here. It looks like we get this, right? So based on those measurements, the estimated BO length, predicted BO length, predicted flipper length, it's going to be around 194.3796. And it's according to the best possible overall models. Now the very last thing, let's check the residual plots. And let's do plot fitted, it's also called predicted values. And we're using model 5A, and also plot residues of model 5A, and also we do AB lines, which is the height equals 0, and the color, each time we do red, okay, and let's close the coding block. Oh yeah, let's actually run one more time, and then we got this, right? It looks like very good diagnostics, approximately normally distributed residues and also residuals as constant values, okay, based on this random scatter plot, right? Concentrated between -15 to 15, somewhere around that. So this again one more time. If you want to comment on the model, the residual plot has good diagnostics, and that indicates there are approximately constant variance and a normally distributed residuals. So that's basically the end of this analysis of a multiple linear regression part 1.